Good evening, everyone. Am I audible? And can you people see me? Any one of you can just unmute your mic and let me know if you guys can hear me.
Yes, ma'am.
Sorry? Hello?
Yes, ma'am.
Yeah, thanks. So let me just share my screen. If you want to say something, you can just unmute your mic and say it out, because I won't be able to see your raised hands and read the chats when once I share the screen. Can you people see the PowerPoint presentation in a slideshow mode?
Yes, ma'am.
Yeah, thank you. So good evening, everyone. For people who have missed the previous session, let me introduce myself. I'm Nisha. I'm one of the TAs assigned to you for the NPTEL course, Drug Delivery, Principles and Engineering, and this is week 2. So have you gone through the week 2 material discussed in the lectures? I need to know whether you have read through it so that we can solve the assignment much more efficiently. Has anybody gone through the lectures?
No, ma'am, I don't know from where it is.
Okay.
From
So
where,
go ahead.
I don't know from where I take that material or read that thing.
So you have joined this NPTEL course, right? There'll be sessions every week, which must be uploaded in the portal. If you check the portal, you will get certain lectures and you'll get new assignments as well to solve. So here in this sessions, we'll be solving the previous year assignment, so that you get an idea of what sort of questions will be asked in the exam at the end of the course. Also, you'll get an idea of how drug delivery aspects are discussed, and how we solve problems in drug delivery. So if you have access to that portal, I think you'll be able to get the lecture material. If not, we'll discuss few of the concepts here as and when we solve the questions. So
Okay,
let's,
ma'am.
yeah. So I'll just give you a recap of what was covered in week 2. So week 2 started with biopolymers, wherein there are two types of biopolymers, synthetic versus natural, and the differences of these were discussed. Also, desirable properties of biopolymers were discussed, the advantages as well as the limitations. In case you want to use biopolymers for a particular disease or a particular medical application, then what sort of questions you need to be answered, like depending on the application, whether you want the biopolymers to be injected, whether you want them to be given orally, or you want to give it via a different route of administration. So those aspects were discussed. Further, certain concepts such as biocompatibility, biodegradability, bioerosion were also discussed. So I'll keep on flipping in between these two screens, as I need to admit other students who are joining late. So just bear with me for a while. Yeah, so also in the subsequent lectures, different kinds of biopolymers were discussed. For example, the class of polyesters, which consists of PLGA. PLGA is one of the most widely used biopolymer, as well as polyanhydrides were also discussed. Next, there is something known as a polymer drug conjugate. So most of the therapeutic drugs, if you see, are either protein or DNA in nature. For example, you have insulin. Insulin is a protein, and people need to take it to control their blood sugar level. So since proteins are very susceptible to denaturation, once you put them in the body, they degrade very faster. That's why you see people taking them very regularly after their meals. So to avoid that, what we can do is we can conjugate these drugs, this protein, with a polymer, so that it slows down its rate of degradation. So some of the advantages and limitations of polymer drug conjugation is also discussed in this week. And one of the examples of such polymers is PEG, polyethylene glycol. And few examples were also discussed if you guys go through the lectures. One more concept known as controlled drug release was discussed in detail. This concept comes in play when you want to give a controlled release of a drug. For example, once you take a pill orally, it will be easily absorbed and most of it will be available in the blood for its therapeutic action. Now, in contrast to this, we sometimes want drug applications to be lasting in the body for a long time. Let's say I take a medicine and I want it to last longer in my body. So what I can do is I can make certain systems such as a reservoir system, wherein it is just a very high concentration of drug which has a polymer around it, and from there it will diffuse very slowly once you inject it in the body. So certain concepts like this were discussed, and we'll discuss some of these as we solve the questions for week 2 assignment. So let me make this clear. These assignments are from previous year courses. We are not discussing any new assignments, but if you guys have any doubts in the ongoing assignments, we can discuss that as well. Also, these sessions are recorded, so and they'll be uploaded on YouTube as well. So in case any of you miss it, you can easily have access to these YouTube sessions. Also, this PPT will be uploaded in a Google Drive, and you'll get the link for the same. So let's start with the new assignment. Before we go on to that, there was one question in the last assignment which we kind of misunderstood. So if people who have attended the first session, they might remember this. Let me go through this question once again. So can everybody see the question displayed on the slide?
Yes, ma'am.
Yeah. So I'll just read through the question. The question says a drug has half-life of 30 minutes in its native form. PEG is conjugated to this drug to improve its pharmacokinetics, and the modified drug is then injected intravenously with an initial plasma concentration of 1 mg per ml. Now, after 12 hours, the concentration of the drug in serum is 0.5 mg per ml. We have to calculate the change in the half-life of the drug after modification, assuming first-order kinetics of elimination. So here is the formula for first-order kinetics. And we did solve this question right to certain extent. So the only thing we missed was they have asked us to calculate the change in half-life, which I remember somebody pointed out very correctly last time. So here you have to solve it using first order kinetics like we did last time. The only change is at the end here. Once we calculate the new half-life, we just have to subtract the previous one from it because they are asking us the change in half-life. If you do that, you'll get an answer of 11.5 hours. So people who have solved it in that way are correct. People who have just written until here, that won't be a right answer. So just take into consideration. I hope it's clear. And can we move on towards the recent assignment? Let me know if you guys have any doubts in this. You can just unmute yourself and speak. If not, we'll move on towards the new questions. So let's go ahead with
Ma'am,
question. Yeah.
ma'am, previous assignment is left to submitted because it is my first lecture. So I can also submitted the previous assignments by completing it.
You mean the week 1 assignment, right?
Yes, ma'am.
Yeah, so there'll be a deadline for the week 1 assignment. If you submit it, I think if you cross that deadline, it won't let you submit it. So I'm not aware of what is the deadline, but before that deadline hits, you can submit the assignment n number of times if you want to change your answers or so. But right now here we are not discussing the new assignments that are going on in the course. These are previous year assignments. But if the for the new assignment, if you have not crossed the deadline, you can still submit it. Just check it with the. You'll be easily able to see it on the portal.
Okay, ma'am.
Is it okay? Yeah. Okay, so let's start with the first question. The first question is for a given polymer, we have to rank Tg, that is the glass transition temperature, Tm, that is melting point, and Tc, that is crystallization point, from lowest to highest. And these are the options. So I'll let you people figure it out for a while. And if anybody is able to answer this, just unmute yourself and let me know the answer. If not, we'll discuss all these three concepts and then see how it is ranked.
And second option.
Second option is TG, TC, and TM. Okay, we have one answer. Does anybody want to give it another try?
Second option, no?
Okay, we have the same answer again. Anybody else? Anybody else has a different answer? if you've read through the lectures, and then you'll be able to know what these three terms mean, and then you'll be able to arrive at the answer. Okay, no more new answers. Yeah, so both of you were right. Whoever answered, I'm sorry I can't see your names. So TGTCTM is the right answer. We'll look at it in more detail. So first of all, let's see what all these three terms mean. Tm is the melt transition temperature. So for any polymer, it is the temperature at which all crystalline regions melt, that is the crystallinity disappears. So for a polymer, it can have both crystalline as well as amorphous characteristics, or there are certain polymers which are strictly crystalline in nature, some which are strictly amorphous in nature. So for a polymer which has both of these properties, this is how the curve looks like. This curve is heat flow versus temperature. So to know what all these TG, TC, TM are, there is a technique known as differential scaling calorimetry. You might have read through this in the lectures. So from this, once you do that experiment, you'll get a curve that looks like this. So as I said, TM is the temperature at which all crystalline regions melt. Glass transition temperature, this mostly applies for polymers which are amorphous in nature. So this is the temperature at which a polymer undergoes a transition from a hard glassy state to a rubbery state. And lastly, crystalline temperature, that is TC, is the temperature at which crystallinity appears. Now let's look at this one by one. I hope you can see my cursor. So once you start heating a polymer, it will first absorb energy and it will go from a glassy state to a rubbery state. It will start flowing. That is when the TG hits. That is the temperature at which it changes from this glassy state to a rubbery state. If you further supply heat to it, so as you increase the temperature, there will be no additional heat flowing from that, but there'll come a point where the heat decreases because so we said that this polymer is now in a flowy state, it's in a rubbery state. So the chains in this polymer, they will start aligning to each other. As they get more and more heat, they will start aligning to each other. There will be a certain order, as a result of which it will start crystallizing. That is when TC appears. Now next, once your polymer has crystallized, if you keep on further heating it, it will then go into its melting temperature where even the crystallinity will start disappearing. So this is the profile you get. So that's why your TG will always be lowest in temperature, followed by TC and then TM. Is this concept clear? People who have doubts can directly ask me. You don't have to wait for you don't have to raise hands or chat. You can just unmute yourself and ask me. Is this clear? I'll wait for a while. Okay, if there are no questions, I'll move ahead to the next question. So I hope you guys can see this question. Second question is, which of the following statements is not a limitation of polymer drug conjugates? We have to choose two right answers. So in other words, this question is asking us what are the advantages of polymer drug conjugates. So I'll let you read the question for a while. Meanwhile, I'll just list out the options. First is biomolecule that is the drug, can lose activity during conjugation process. Purification of unreacted polymer, biomolecules and any reaction products is necessary before in vivo application. Sterilization process now involves polymer stability. This can be viewed by regulatory authorities as a new drug entity. Polymer drug conjugates can improve bioavailability of many poorly soluble drugs. If not compatible, they can trigger inflammatory reactions. Polymer drug conjugates can be targeted for specific applications. So if anybody knows the answer to this, you can just
Ma'am, option 5 and 7, ma'am.
5 and 7. So 5 is polymer drug conjugates can improve viability and polymer drug conjugates can be targeted for specific. Okay, we have one answer. Anybody else wants to give a try? I'll wait for others to read through the options. Anybody has any other answer apart from option 5 and 7? Okay, so I'll just display the answer. So yeah, whoever answered option 5 and 7 is the correct one. So let's just discuss this concept in a bit more detail. So as I said, polymer drug conjugates, this concept is there because we don't want our there are two applications. One, if your drug is very hydrophobic, I mean it's not solubilizing and you want it to solubilize faster, that's when you can conjugate it with certain polymers which are hydrophilic in nature. For example, this is one such example where you conjugate your drug with PEG, that is polyethylene glycol, which is highly hydrophilic in nature, that will increase the solubility of your drug. Also, if you don't want your drug molecule to go away faster, you don't want them to degrade, then also you can conjugate it with polymers, which will then reduce the access of enzymes in your body, because they'll form like a brush kind of thing, and they'll just brush off whichever enzymes come near it, and they won't let your drug to be degraded. Now, there are two ways in which you can conjugate your drugs. One, if your drug is a very small molecule, what you can do is you can take a long polymer chain, and you can using certain chemistries, you can conjugate these drug molecules to its backbone. And then whenever so this chain, this linkage can be hydrolytic in nature, meaning that water can easily act on that and break this linkage, or it can be acted upon by an enzyme. In that case, whether by the action of water or enzyme, these drug molecules will be free to act. If your drug is a very big molecule like a protein, then you can conjugate polymer on its surface. So there are two ways in which polymer drug conjugates can work. There are certain advantages associated with this, two of which we discussed. One is it can increase solubility for hydrophobic drugs, and it can reduce the rate of degradation of these drug molecules. Also, as we have discussed in the last assignment, if you guys remember, so the smaller particles which are smaller than 10 nanometer or around 10 nanometer, can be quickly cleared out by kidney filtration. So if you want to increase the size of your protein, you can conjugate it with polymer chains like this, that will make it higher than 10 nanometer, and kidneys won't be able to clear it out. So I hope this answer is clear to you and you have no doubts in this. If any, you can ask away. Any doubt in the recent question? Shall we move ahead? Okay, if no more doubts, I'm going ahead with the next question. Okay, question 3 is, a gold surface was grafted with a polymer. The ends of this polymer are tagged with four pendant groups, namely A, B, C, and D. The pendant groups are weak acids, and the modified isoelectric point of the entire polymer is given as follows. Next, these particles are loaded with a positively charged drug on the surface using electrostatic interaction in a PBS which has a pH of 7.4. Now they're asking us which of the following will have minimum loading, and these are the options. So I'll give you guys some time to read this again carefully, and then if anybody has arrived at the answer, you can tell me.
Ma'am, option D, ma'am.
Option B, that is polymer B, is it? 5.5. Okay. Anybody else has an answer? Any other answer from option B? Shall we discuss the answer? Okay, so the correct answer is option D. We'll see how that is the right answer. Before that, does anybody know the concept of isoelectric point?
Ma'am,
Yeah, so isoelectric point is mostly concerned with proteins and amino acids, though it is applied to other molecules as well. So isoelectric point is a pH at which molecule carries no net charge. So if you consider this point as the isoelectric point, then we have to figure out what happens below and above it. So if the pH of your pH surrounding the molecule is higher than the isoelectric point, then it is going to carry a negative charge. If the pH of the surrounding environment is lower than the isoelectric point, the molecule is going to have a positive charge. So the question is, these particles are loaded with a positively charged drug, meaning if you want to have minimum loading, then your polymer as well as your drug should be positively charged. So essentially the question is asking us, amongst these polymers, which of the polymer is going to have a positive charge at pH 7.4, because the surrounding pH will be the pH of this PBS. So if you carefully look at these options, 7.4, let's first eliminate the least probable answer. If you have a pH of 7.4 and your isoelectric point is also 7.4, it means the polymer, the molecule is going to have a neutral charge. Now compared to the rest of the polymers, let's say polymer A, that has a isoelectric point of 4.5, which is lower than its so so the pH is actually higher than the isoelectric point. So that is going to give us a negative charge. It means your molecule is going to have a negative charge. Next polymer is polymer B, that is 5.5. This also, the surrounding pH will be higher than its isoelectric point. If we consider surrounding pH as 7.4, again this polymer is going to have a negative charge. Now if the polymers have a negative charge and your drug has a positive charge, there is going to be a very strong electrostatic interaction. So both of these polymers will have a high drug loading. Now compared to all these three, if you see polymer D, which has an isoelectric point of 9, here the surrounding pH will be lower than the isoelectric point. So that means if we go lower, then the molecule is going to have a positive charge. So positive charge will repel, and as a result of which your uh, polymer D is going to have the least loading. Does this answer make sense to you? Oh, you lost connection. I'm sorry, I lost internet connection. Can anybody tell me till where you heard me? Hello? Yeah, can anybody please tell me what we were discussing? Because I lost the internet connection. I couldn't see what.
Isoelectric point, ma'am.
Okay, sure. Thank you. I'll share my screen again. Yeah, so I hope you guys can see the screen now. Okay, we'll go over this concept once again. So isoelectric point, as I said, is a pH at which the molecule carries no net charge. So, and we know from the protein and amino acid studies that at a pH, if the surrounding pH is higher than your isoelectric point, your molecule is essentially going to have a negative charge. And vice versa, if you have a surrounding pH lower than your isoelectric point, then your molecule is going to have a positive charge. Now let's go over the options once again. Yeah, so here if you see your polymer A has a pI of 4.5. Now, if you see your pH, the surrounding pH is definitely the pH of the PBS. That's where your drug is going to be. So that pH is higher than your isoelectric point, as a result of which that polymer is going to have a net negative charge. If you consider polymer B, the pI is 5.5 compared to the surrounding pH. Again, your pH of PBS is 7.4, which is higher than 5.5. As a result of which, again, polymer B will also be negatively charged at this particular pH. Let's look at option C, that is 7.4. This is the same as your isoelectric point, and hence, when pH equals your isoelectric point, the polymer is going to be net neutral charge. Now, compared to all these three, if you see your polymer D, which has an isoelectric point of 9, now, if you compare the pH of your surrounding, which is actually lower than pI, then that's when your polymer is going to have a positive charge. Now, the question is asking us which of the following will have a minimum loading. Now, our drug is positively charged, so definitely the polymer which will be positively charged at this particular pH is going to have a minimum loading because there will be repulsion. So that's why the correct answer is D. I hope I've made this clear. Do you guys have any doubts in this? Has anybody not understood? You people can unmute yourself and let me know if you have understood this question and this concept.
Yes, ma'am.
Okay, you can stop me at any point and ask any other questions related to the same question. So we'll move on towards the next. Okay, so the next question is which one of the following polymers degrade hydrolytically by near zero order kinetics? And several polymers are listed out in the options. I'll give you guys a minute to read this, and if anybody has the right answer, you let me know, or rather any answer.
Ma'am, as per surface degradation, it's option 3, ma'am.
Sorry,
As per surface degradation, it's option 3, ma'am.
option 3, which is polyanhydrides. Okay, we have one answer.
Yes.
Does anybody else wants to give a try? Okay, no other answer? Yeah, so the right answer is polyanhydrides because as somebody pointed out correctly, they degrade from the surface. So this is the polyanhydride functional group. So these polymers are very sensitive to water, as a result of which they start degrading from the surface, and because of that they follow zero order release kinetics. Are there any doubts in this? This is a pretty straightforward question. If you have read through the types of polymers uh, session in this week, you'll get this. Shall we move on? Okay, I'll go to the next question. Next question is, which of the following are correct with respect to PLJ particles? We are supposed to choose two correct options. So the options are, it is a non-biodegradable polymer. It can be used as a vehicle in gene therapy. They can degrade at gastric pH. They have not been used clinically. It is not a copolymer. They can be extracted from chitosan based products. Does anybody have
Option 2 and 3, ma'am.
option 2 and 3? Okay, any other answer? I'll give you guys some time to read through the options.
Ma'am, is it A and C?
A and C. Okay, we'll discuss through the options once again. Hold on for a while. Anybody else has an answer? So we have two answers, option B and C, and another person said A and C. Any other answer apart from these two? Okay, let's look at the answers. So whoever said C is the correct option, and we have another option that is B. So let's see what PLJ is. So as I said, PLJ is from the class of polymers belonging to polyesters, and it can be hydrolyzed easily by acids and bases. So if you see the first option, we'll go option by option. So is it a non-biodegradable polymer? Definitely not. It will degrade. It is a biodegradable polymer. It won't stay in your body for a longer time because it is hydrolytically cleavable. Next, it can be used as a vehicle in gene therapy. It is very widely used because when you're giving gene therapy, your gene is essentially DNA, and that is very susceptible to denaturation. So what people do is they incorporate this gene in a PLGA polymer, and that's how it's delivered. Third option is they can degrade at gastric pH. So if we see gastric pH is very highly acidic in nature, and since PLGA has can be catalyzed by acids and bases, that is why PLGA gets degraded at gastric pH. Next, they have not been used clinically. No, that is again a wrong option. They are very widely used clinically. Is it not a copolymer? No, PLG is a copolymer of glycolic acid and polylactic acid. And next is they can be extracted from chitosan based products. No, PLG is not natural polymer. It is synthesized chemically. So it essentially is a chemical polymer. Are the options clear? Does anybody have any confusion in this? Any doubt in this? No questions, no doubts until here. Shall we go ahead?
Yes, ma'am.
Okay. So the next question is, what are the advantages of using polyethylene glycol in drug delivery applications? And following are the options. Here also we are supposed to choose two correct options. The options are, has well developed conjugation chemistries, is non-toxic, immunogenic, and can be produced under GMP, highly hydrophobic and biocompatible, can be easily phagocytosed by immune cells, can deliver cargo intracellularly very efficiently. So, does anybody have an answer? You guys can take your time reading through the options.
Option 1 and 2, ma'am.
Option 1 and 2. Okay. Any other answer? Anyone else wants to give it a try?
Option 2 and 3, ma'am.
Option 2 and 3. Okay. Anyone else? We'll wait for others to answer. If not, we'll discuss. Okay, so the correct answer is option 1 and 2. So we'll discuss why these two are the correct options. First is has well developed conjugation chemistries. So yeah, that is one of the correct options. That is why PEG is so widely used, because it's easy to conjugate drugs to PEG. Next is it is non-toxic. There is a printing mistake in this question. It should be non-immunogenic. So it is non-toxic, non-immunogenic, and can be produced under GMP. So uh, the process to conjugate PEG and scale it up for a large scale application is fairly standardized. And the third option is it is highly hydrophobic and biocompatible. Half of the answer is right. It is biocompatible, but it is not hydrophobic, because polyethylene glycol is has a lot of hydrolytic bonds in it. So it is highly hydrolytic. Next is can be easily phagocytosed by immune cells. No. So PEG is branched in nature. So let's say you have these branches of PEG on your particular protein or your drug. So since they're brushes and there's a lot of fluid movement happening here, they just keep on waving inside this fluid. As a result, they will not let the larger cells, that is your immune cells, come near this drug molecule. So as a result, they will avoid phagocytosing. So this option becomes wrong, that it cannot be easily phagocytosed by immune cells. And the last option is can deliver cargo intracellularly very efficiently. Now, if this cargo has to be delivered intracellularly, this entire thing has to go inside a cell. And as I said right now, because of the branched nature of PEG, it will not allow cells to come near this drug molecule. So it won't be taken up very easily by the cells. So as a result, PEG cannot be used to deliver cargo intracellularly much more efficiently. So the right option is it has well-developed conjugation chemistries and it is non-toxic. Any confusion here? I hope this is clear.
Yes, ma'am.
Okay. Okay, then I'll move on towards the next question. Next question is, if a particle takes time t to diffuse lmm, how long will it take to diffuse 4 lmm? Sort of like a numerical. And if you guys have read this concept of diffusion, then you will be knowing that there's a particular formula to solve this question. These are the options. I'll give you guys some time to just grab paper and pen and try solving it on your own. If anybody has an answer, we can discuss. If not, we'll
Option
go.
4, ma'am.
Okay, option 4 is 16t. Okay, anybody else has an answer? We have one answer as 16t. I'll wait for a while for others to solve it. Anyone else wants to volunteer before we go towards the solution? Okay, so yeah, 16T is the right answer. We'll just quickly go over the solution. So there is something known as root mean square displacement, and this is the formula for it. X is equal to under root 2 dt. So here d is your diffusion coefficient, t is the time taken for the molecule to diffuse. Now if you see, we have given the information that in time t it diffuses lmm, and we have to calculate how much time will it take to diffuse 4 lmm. So if you just write this expression and take a ratio of these two expressions, you'll quickly see that it takes somewhere around 16t. Is the solution clear, or is there any confusion? So you won't need the diffusion coefficient here, the value of it, because it's the same molecule diffusing, so your dd will get cancelled. Does anybody have a doubt here? So this question essentially tells you that even if you, let's say, the thickness, suppose your drug is in a polymer membrane, and your polymer membrane has a thickness of, let's say, lmm, and you change it to 4 lmm, your time is going to be squared. So it will take much more longer time for the molecule to diffuse. Any doubts in this question? Pretty straightforward if you know the formula. Want me to go ahead? Okay. Okay, so the next question is, consider that a drug A is loaded into two separate reservoirs whose drug releasing areas are in the ratio 2:1, and the loading concentration of drugs are in the ratio of 1:2. Now, what is the ratio of mass of drug released in the same amount of time for these two reservoirs? Assume that the reservoirs are flat and non-erodible. The drug diffuses through a semi-permeable membrane in both the cases. I'll give you guys some time to carefully read through the question, solve it, and then let me know the answer. Anyone trying to say something?
And the screen is not updated, ma'am.
Sorry?
The screen is not visible, ma'am, for 8th question.
You guys can't see the screen?
8th question we can't see, ma'am. It's up to 7th question.
Oh, okay. Now can you see it?
No, ma'am.
Is it the problem with you, or everybody else is facing this?
No, ma'am, I can see the eighth question.
Ah, okay. Might be some issue with your internet connection, the one who is not able to see it. Maybe try joining again. Okay, the answer is fairly displayed, but I'll still give you guys some time to solve it. Can you see it now? Others can see it, right?
Yes, ma'am.
Okay.
Ma'am, it's option 1, ma'am.
No, there are no options. I mean, you're saying
Ma'am,
the
it's answer 1, ma'am.
okay, okay, yeah, right. Yeah, the answer is one. We'll look at the solution one by one, step by step. So we have this formula. If you have if you have gone through the lecture where the professor is discussing the drug reservoir, you can see there is a formula which essentially tells us the mass of drug released is directly proportional to the area of the reservoir. D stands for the diffusion coefficient of the drug. K is the partition coefficient of the drug. Cs is the solubility of the drug. C naught is its initial concentration divided by L, that is the thickness of the reservoir, and the time. So since it's the same drug uh, in both the cases, we can just easily cancel out D, K, and Cs because that is the drug specific property that won't change as you change the reservoir. Now what we have been given is we have the ratio of the areas of these reservoir, that is A1 is to A2, that is 2 is to 1, and we have the ratio of drug loading, that is C0 1 is to C0 2, that is 1 is to 2. Here we can ignore the L variable because it is mentioned that your reservoirs are flat, so the thickness can be neglected. If you then take this expression and take the ratio of these two expressions, you will see that these two values cancel each other out and the answer is 1. Any doubt in this? So even if you change the areas and the drug loading concentrations in the same ratio, same amount of mass of drug will be released from both these reservoirs. If you guys have any doubts, you can ask. Is it clear? You can hear me, right?
Yes, ma'am.
Okay. And the screen is also visible. Okay, if no more doubts, I'll go ahead with the ninth question. So the question is, consider a microsphere of diameter 1 micron. Calculate the number of such particles that would be present in 1 mg given the density of the material is 1.3 gram per ml. And there are two right options in this question. So I hope you can see the question and the options as well. So just take some time, solve it, and let me know if you have the answer.
Ma'am, option 1 and 3, ma'am.
Option 1 and 3. Okay, we have one answer. Anybody else wants to give it a try? Shall we discuss the solution? So option 1 and 3 is the correct answer. Let's look at the solution. So what we have been given, we have the diameter of the microsphere and we have its density, and we have given a certain amount of this microsphere, that is 1 mg, and we want to calculate how many particles of this microsphere will be there in 1 mg. So first of all, you need to calculate the volume. So here just be careful that diameter is given and you have to first get to the radius. When I solved it first, I solved it completely wrong because I took diameter as it is. And pay some attention towards the unit conversion as well. So what I've done is I have taken the radius, I have converted micrometer to centimeter, so that when it becomes centimeter cube, that will be in ml. So I can easily cancel out the units. So volume of one particle, as we know, it's a sphere. So its volume will be 4 by 3 pi r cube. You can just put in the value and you'll get this volume. Next, we have to calculate the mass of one particle so that we know how many particles will be there in 1 mg. So if you just do multiply the density and the volume, you'll get a mass in grams. We have to convert it to mg because the amount which we have with us is in mg. So you'll get a value for the mass of one particle. Now to calculate number of particles, you just take whatever amount you have with you divided by the mass you got, and then you'll get this answer. So it's somewhere around 1.47, which is what I got from my calculator. So this is, the options are much more precise. And if you want to convert it to this unit, it will be 0.147. Is the solution clear? If you guys have any doubts, you can ask. Anybody has any questions on this? If not, we'll move on towards the next question. So this is the last question in this session. The question is, reservoir system refers to, following are the options: a system saturated with drug surrounded by a degradable membrane, all systems with zero order release rate, all systems with first order release rate, systems which have a non-degradable membrane and are supersaturated with the drug, all systems with second order release rate, systems with a semi-permeable membrane which degrades with time. Anybody wants to give it a try?
Option 4, ma'am.
Option 4, systems with, okay. Yeah. Any other answer? Just read through the options once. Yeah, that option 4 is the right answer. Systems which have non-degradable membrane and are supersaturated with drug. So let's look at the reservoir system in some detail. So it is essentially, as I said, a supersaturated drug reservoir which is surrounded by a non-degradable polymer membrane. So what you do is you take your drug at a very high concentration surrounded with a polymer membrane which does not degrade. So this system comes under the diffusion controlled, as I was discussing at the start of the session. This is one of the methods where you can achieve controlled drug release. So your drug will have certain diffusion in the surrounding area. So since your polymer is porous and it is non degradable, your drug will eventually diffuse out in a slow fashion because there is a lot more concentration inside compared to what there is outside. So this system can have a planar configuration, meaning the reservoir of the drug is in between two membranes, or it can have a cylindrical configuration. And most commonly used polymers in this are silicone and EVAC. And because it releases at a constant rate, it has a zero order release rate. Zero order release rate meaning the rate of your release will not be dependent upon how much concentration of drug is inside the reservoir. It will flow off at a constant rate. Is this clear?
Yes, ma'am.
Okay, so these are the questions for this particular assignment. Does anybody have any doubt in the questions we discussed? You can just unmute yourself and let me know if there are any doubts. For people who, yeah, anybody trying to say anything?
Ma'am, can you please repeat question number 2, because during that I had some network issues and I couldn't follow.
Okay. So for you as well as for people who joined a little late, I'll go through the questions once again. Stop me wherever you
Thank
have
you,
to.
ma'am.
Yeah.
Thank you.
Yeah, so the first question is, for a given polymer, we have to rank Tg, Tm and Tc from lowest to highest. And the right order is Tg, Tc, Tm. That is, Tg is the lowest, followed by Tc, Tm is the highest. So here we said that this is the graph which you get if you subject your polymer to differential scanning calorimetry technique. Here Tg is mostly for amorphous polymers, where once you increase the heat supply to the polymer, it changes from a glassy state to a rubbery state, followed by it will, if you still keep on increasing the temperature, it will then align itself. The chains which are flowing, which are in this flowy rubbery state, they will start aligning themselves. They'll have some order. That's when they start crystallizing. That is the TC point, the crystalline temperature point. Then if you still keep on further heating, increase the temperature of this polymer, it will then reach a stage where even the crystallinity will start disappearing. That is, it starts melting, and this is where all your chains will be melted, and that's the melt transition temperature. So if anybody ever asks you the order of these, it is always Tg is the lowest, followed by Tc, and Tm is the highest. So next, this is the question. Which of the following statements is not a limitation of polymer drug conjugates? And we have to choose two statements. So polymer drug conjugation is a technique where you want to change the properties of your drug. If your drug is hydrophobic, you want to make it more hydrophilic. That's when you conjugate it with certain polymers such as PEG. Contrast to that, if you want the slow degradation of your drug, then also you can conjugate it with polymers that will avoid its degradation. So here this question is asking us the advantages of polymer drug conjugates. You have to read the question carefully. It is not a limitation. That means it's asking us the advantages, and the advantages are polymer drug conjugates can improve bioavailability of many poorly soluble drugs. As I said, you can conjugate the drug with polymers, and then that with hydrophilic polymers, that will increase its solubility. And the next right statement is polymer drug conjugates can be made targeted for specific applications. Is this clear? Was this question somebody had an issue with the internet connection? Was it for this question?
Yes, ma'am, it's clear.
Yeah. Okay. Thank you. Then next question was, a gold surface was grafted with a polymer. The ends were tagged with 4 different pendant groups, A, B, C, D, which are weak acids. And the modified isoelectric point of the entire polymer was given to us. And we have been asked that these particles are loaded with a positively charged drug on the surface using electrostatic interaction in PBS, which has a pH of 7.4. Now we were asked which of these pendant groups will have the minimum loading. So since your drug is positively charged, the polymer which will be positively charged at this particular pH will have the least loading. And as you know, isoelectric point is the pH at which the molecule carries no net charge. And above and below, if your pH is above isoelectric point, the molecule will be negatively charged. If your pH is below isoelectric point, it will be positively charged. So amongst these options, only option D has an isoelectric point of 9, for which the surrounding pH is lower than the isoelectric point. As a result, only D polymer will be positively charged. As a result of which, the positively charged drug will have a repulsion for this pendant group, and that's why it will have the minimum possible loading. Everybody else will have more loading compared to polymer D. I hope this question was clear. If anybody has doubts, people who joined later on, if you want me to discuss this in further detail, we can do so. Just stop me wherever you feel confused. Next question was, which one of the following polymers degrade hydrolytically by zero order kinetics? The right answer was polyanhydrides, because they follow surface degradation. As a result, it gives a zero order release kinetics. Next question was, which of the following are correct with respect to PLGA particles? And the right option was they can be used as a vehicle in gene therapy, and they can degrade at gastric pH, because PLGA comes from a class of polyesters. They are easily hydrolyzable by acids and bases, and since gastric pH is highly acidic in nature, it can easily degrade PLG. Also, PLG is widely used as a vehicle in gene therapy to avoid denaturation of your gene. Next question was, what are the advantages of using polyethylene glycol in drug delivery application? The right option was, it has well-developed conjugation chemistries, it is non-toxic, non-immunogenic, and can be produced under GMP. The rest of the options are not correct because even though it is biocompatible, PEG is highly hydrolytic in nature. Also, it cannot be easily phagocytosed by immune cells because PEG has a branch kind of character, and as a result, it will not let your immune cells come near this drug molecule. Also, because of this reason, it cannot be used as a it cannot be used to deliver cargo intracellularly very efficiently because it will be difficult for cells to just gobble up this molecule because of the branches of PEG. Next question was, if a particle takes time t to diffuse L how long will it take to diffuse 4 L This comes from the concept of diffusion and root mean square displacement. So this is a straightforward formula where your root mean square displacement is equal to under root 2 dt. The diffusion coefficient here will remain the same because it's the same particle. If you just take the ratio of these two expressions, you will get the modified time, the time it takes to diffuse 4 L That is, the correct answer is 16t. Next question was, we have been given a numerical. Consider that a drug A is loaded into two separate reservoirs whose drug releasing areas are in the ratio 2:1 and loading concentration of drugs are in the ratio 1:2. What is the ratio of mass of drug released in the same amount of time for these two reservoirs? We have to assume that the reservoirs are flat and non-erodible. The drug diffuses through a semi-permeable membrane in both the cases. For this also, we have a formula where the mass of drug released is related with the area of the reservoir, the diffusion coefficient of the drug, partition coefficient of the drug, CS is solubility of the drug, C0 is the loading concentration of the drug, L is the thickness of the reservoir, and the time. So D, K, and CS become irrelevant because it's the same drug in both the cases. So we have been given A1 is to A2, that is the ratio of the drug releasing areas as 2:1, and C01 is to C02, which is the loading concentration, ratio of loading concentration. L is negligible here because we have assumed that the reservoirs are flat. There's no thickness to that. So if you just put this for expression, take a ratio of it, you will arrive at the answer 1, which is within the range of the right answer. Okay, next question was, consider a microsphere of diameter 1 micron. Calculate the number of such particles that would be present in 1 mg given the density of material is 1.3 gram per ml. So we have been given the diameter, we know the density. So we have to calculate how many particles will be there in 1 mg. For that, we first must know the mass of one single particle. For that, we can easily calculate the volume since you have the diameter. Volume of a sphere is 4 by 3 pi r cube, and just put it in the formula and you will get the volume. So before that, you need to convert this micron into centimeter so that when you get centimeter cube, it will be equal to ml, volume of one particle. Next, we have to calculate mass of one particle, which we can do by density into volume. You'll get the mass in gram, convert it into mg. Since you have an amount of 1 mg, to calculate the number of particles, you just divide the given mass by whatever you have got, and you will get an answer of 1.47 into 10 raised to 9, which is similar to the first option. And then if you want to convert it to 10 raised to 10 unit, you get the third option. And the last question was, reservoir system refers to, we have been given several options. The right option is, these are systems which have a supersaturated drug reservoir and they are surrounded by a non-degradable polymer membrane. So we just went quickly, had a recap of this assignment. So do you guys have any doubt in this? You can raise your hand. Now I'm able to see the screen and I can also see the chat box. So if you guys have any doubt, you can let me know. In this assignment or in, so you must have submitted the first assignment, right? Has anybody done that in the the ongoing course? We can also discuss the new assignment for week 1, which is already submitted, if you have any doubts in that. Or if you have doubts in the ongoing lectures, we can discuss that as well. If there are no doubts, then we can end this session. Next week, we'll be following up with the week 3 assignment from the previous courses. Before that, once you go through the material, let me know if you guys have any doubts. We can discuss it in the next session or in the current session. Anybody has any doubts? If not, we can stop this session. You will the recordings of these sessions for week 1 as well as week 2 will be available on YouTube. You'll be getting the link, as well as the PPT which we just discussed will also be uploaded in a Google Drive, and you'll get the link for the same. Thank you. If there's nothing else to discuss, we can stop this meeting.
Hello.
Yes.
Ma'am, I have joined late. Can you please explain first 3 questions, please?
Yeah, sure. Let me just share my screen again. Can you see the first question?
Yes, yes.
Yeah, so the question is, for a given polymer, we are supposed to rank Tg, Tm, and Tc from its lowest to highest. So have you read through the first week, the second week material?
Yes, yes.
Yeah, so the answer here will be Tg, Tc, Tm, because
Right.
yeah, we get this graph, and for polymers which are more amorphous in nature, we'll first get Tg, which is the glass transition temperature, where if you
Okay.
start heating the polymer, the polymer will start from a glassy state to a rubbery state, and this Tg will increase. If you further heat it, you will reach a point called Tc, which is the crystalline temperature. Now, because your
Okay.
polymer is in a flowy state, it will have its polymer chains, and they'll start aligning against each other. There'll be some order there, and that's when it starts crystallizing first. So after crystallizing, if you still keep on heating it, that's when your melt transition temperature will be hit, because if you further keep on heating a crystalline temperature, a crystalline polymer, it will start melting. That's when the crystallinity disappears. So that is the highest. So if you have to arrange them from lowest to highest, it will always be Tg followed by Tc followed by Tm. That's the answer. Is this clear?
Yes, ma'am.
Yeah. So the next question we have was, which of the following statements is not a limitation of polymer drug conjugates? We have to choose 2 statements. So the right answer was, polymer drug conjugates, they can improve bioavailability of many poorly soluble drugs. For example, if your drug is hydrophobic in nature and you conjugate it with PEG chains, which is polyethylene glycol, which is highly hydrophilic, if compared to your drug, if you have more number of these hydrophilic chains surrounding the drug, the ultimate solubility of your drug molecule will be increased. So even if your drug is hydrophobic, because you have this hydrophilic chain surrounding it, it will be more soluble. So that's why, since it is being more soluble, it will be more bioavailable as well. That is the first option. And next right answer was polymer drug conjugates can be made targeted for specific applications. So
Okay.
depending on the applications, you can choose what polymer you want to conjugate with your drug, and that will give you most effective treatment. So that was question 2. And question 3 was we had a gold surface which was grafted with a polymer, and the ends of this polymer were tagged with 4 pendant groups, namely ABCD, which were weak acids. And they've calculated the isoelectric point for the modified polymer, and for 4 pendant groups, the isoelectric points is listed here.
Madam, in
Yeah,
green only two, question number 2 I can see.
you can't see question 3.
Yes.
Okay, I think it's the poor connection.
Okay.
Anybody else can see the screen? I just want to know if you guys can see the screen. Can
Now
you?
screen is visible. Now it is visible.
Okay, you can see question 3, right?
Yes.
Yeah, okay. So yes, we have this polymer with 4 pendant groups, A, B, C, D, and they have given us the isoelectric point for these 4 pendant groups. And the question is, these particles are loaded with a positively charged drug on the surface using electrostatic interaction in PBS, which has a pH of 7.4. And we have to give the answer for which pendant group will have the minimum possible loading. Do you know the concept of isoelectric point?
Yeah, little bit.
Okay, yeah. So isoelectric point is the pH at which molecule carries no net charge. So if your pH equals your isoelectric point of the molecule is going to have equal number of positive and negative charge. As a result, the net charge will be 0. But if the pH of the surrounding of that molecule is more than your pi, that is the isoelectric point, the molecule will carry a negative charge. And if the pH is lower than the pi, it will carry a positive charge. So if you see the options here, let's first look at option C, I mean the polymer C, the pi is 7.4, which equals the pH. It means it will carry a neutral charge. So first of all, let's understand the question. To have minimum loading, since your drug is positively charged, your polymer, if it is positively charged, it will start repelling each other. And that's when you will have minimum loading. I hope I'm making sense. Is this clear?
Yes.
Yes. So now let's look at it one by one. So for your pendant group A, the isoelectric point is 4.5, and your pH is higher than the isoelectric point, which means the polymer is going to have a negative charge. Similarly, for your group B, which has an isoelectric point of 5.5, that is also, so the surrounding pH is again higher than your isoelectric point. So your polymer B will also have a negative charge. Now, if these two polymers have negative charge, your drug having a positive charge, that will be a very strong electrostatic interaction, and that will give you a higher loading. But the question is asking us which will have minimum loading. So if you look at the polymer D, which has an isoelectric point of 9, so here your pH will be lower than the isoelectric point. That's when your pendant group will have a positive charge. Since your drug is also positively charged, polymer is positively charged, there'll be repulsion, and that's why you'll have minimum loading. So the correct answer
Got
is
it. Yes, yes. Got it, ma'am. Thank you.
yeah. Okay. Anybody else has doubt in any other questions or wants me to repeat any solution? If not, then we can stop this session.
Yes. Thank you, ma'am.
Most welcome. Okay, then see you all in the next week, next Tuesday, with the new assignment. Thank you. I'm going to stop the meeting now.